So before we get started today, I had planned a lab exercise after we do this review on Le Chatelier's principle. The problem is that someone has used up all of our disposable gloves and not replaced them. And Le Chatelier's principle, the method that we're using, requires that we use some hazardous materials. And we can't do that without protection. So I sent an email to the whole class, and what we're going to do is this lab is going to be completed online. There is a demo, there's an introductory demo, and then there's an actual lab demo where I do the lab myself, if you've seen them before, with my little GoPro camera. And so what you need to do is print out the document, the method, and then as I proceed through the lab, fill in the observations, answer the questions, do any other things that are required, and submit that online or in person. Next week is our final exam on exam number 4, actually, on chapters 9 and 10. So you can bring it to class if you want to take the test on paper. If you want to take the test in Brightspace, then you'll need to submit this lab online in Brightspace. All right. So let's take a look at this review document, which is also in Brightspace. And this chapter 9 and 10, we're going to do chapter 9 first. And numbering restarts with chapter 10. So I'll have to be sure and change this identifier so that we'll know number 1 from chapter 9, not number 1 from chapter 10. All right, so let's see what we got going here. Number 1. Which of the following general reaction types is characterized by there being a single reactant? Remember when we went through the reaction types, our generic reaction said this reactant would produce those two. So that doesn't mean that we have necessarily elements produced from a compound. These could be simpler compounds from a more complex compound. That's the idea here. So complex makes simple. So the one that satisfies that is a decomposition. We're just breaking that reactant down, and it doesn't have any other reactants in its neighborhood except for its own neighbors, other ABs floating around. It might smash into those, and that's probably what happens to break those bonds. But the complex makes simple, and that's a decomposition. All right. Number 4. Let me see if I want to be sure I'm not chopping something off over there. Yeah, okay, we're good. Number 4. The proper assignment of oxidation numbers to the elements in the polyatomic ion SO3 2-. Okay, oxidation states. Remember those that we fixed. Remember, oxidation state determination is a bookkeeping scheme for our electrons. It doesn't necessarily mean that there's a charge. It just means that this is where we're assigning the location for our electrons. And we said that oxygen is always a 2- oxidation state. Right? So if we got 3 of them, that means we have a total of 6- oxidation states. But we also know that when we add them all up, they have to be equal to that charge. If there is a charge, the oxidation states must add up to that charge. So the way I do this is I say, okay, I need to balance 6 minuses, except two of them don't need to be balanced. So I really only need to hold out 4 minuses to be balanced by this sulfur. Okay, and you can check it out. Right, 3 times 2 minus is 6 minus, plus 4 plus is 2 minus. So we have a 4 plus for the sulfur and a 2 minus for the oxygen. And that's why the answer is D. All right. Number 6. Which element is oxidized in the following redox reaction? All right, I'm going to write it down here so I can have a little bit more room. So we have 2 hydrogen sulfide, and we have 1 oxygen, and that's going to produce 2 water plus 1 sulfur. Now, first question I always ask myself, is that thing balanced? It should be, but we don't know for sure. Let's see, 4 hydrogens, 4 hydrogens, 2 sulfurs. Oops. That needs to be a 2, doesn't it? Okay, so that equation is not balanced. 2 oxygens, 2 oxygens. Okay, now the question is, which element is oxidized in the following redox reaction? Remember our mnemonic device. Right? Oxidation is loss of electrons. Reduction is gain. So if we're looking for the one that is oxidized, we want the one where electrons have been lost from one side to the other. So in order to do that, we have to determine the oxidation states of all the elements in this compound, in this reaction. So sulfur is always a +1, unless it's combined with a metal. If hydrogen is combined with a metal, then it's a -1, because the metal wants to give up electrons more than hydrogen wants to. So hydrogen has to accept it. But in this case, that's a non-metal. It wants to be negative. This one has to be positive. So we have 2 pluses here. That makes this one 2 minuses, right? Elements in their most common stable form at room temperature and 1 atmosphere pressure are always 0, right? So that means this one is also 0. And how about water? Well, we just said oxygen is -2, right? And hydrogen is a +1. Right, so there we have all of our components have been assigned values of their oxidation states. Which one is oxidized? Which one lost electrons from here to here? Well, let's see. Oxygen went from a 0 to a 2 minus. It gained electrons. Sulfur went from a 2 minus to a 0. It lost 2 electrons. So this is the compound that was oxidized. So the sulfur in hydrogen sulfide is oxidized from a 2 minus state to a 0 state. All right. Number 7, see if I can squeeze both of them, 7 and 8. Which substance functions as a reducing agent in the following redox reaction? What is a reducing agent? A reducing agent is the oxidized whatever is oxidized serves as the reducing agent. It causes the reduction of something else. That's why we call it a reducing agent. So we need to look for the one that's oxidized. All right, so we have methane plus oxygen. By the way, what type of reaction is that? If we got oxygen in it, that's a combustion. It's also an oxidation reduction reaction. And two waters. Okay. Did I lose somebody? I think I did. All right, let's see if this is balanced first. Carbon, carbon. 4 hydrogens, 4 hydrogens, 4 oxygens. 2 plus 2 is 4. So that one's balanced. Which substance is oxidized, functions as the reducing agent? Well, let's see. This one's 0 because it's an element. This one is a 2 minus. This one is a 1 plus. This one is a 2 minus, which means 4 minus total, which means this one is a 4 plus. This hydrogen is a +1 because it's bound to a non-metal. So that means 4 pluses here, 4 minuses there. All right. So which one was oxidized? Which one lost electrons? We went from carbon 4 minus to a 4 plus. How many electrons do you have to lose to go from a 4 minus to a 4 plus? Well, to get to 0, you have to lose 4, correct? But then go to 4 plus, you have to lose 4 more. So you have to lose 8 electrons for each carbon. And that's our oxidizing agent. Reducing agent, excuse me. Our reducing agent is methane. All right. Let's look at number 8. What's the change in oxidation number for cobalt in the redox reaction? Okay, so we have 2 CH203, and then we have 3 carbons, and then we have 4 cobalts and 3 CO2. Okay, let's see if this one is balanced. Let's see, we have 4 cobalts, 4 cobalts. We have 6 oxygen here. We have 2 times 3 is 6. 3 carbons here, 3 carbons there. So we're balanced. What's the change in oxidation number for cobalt? So cobalt, we don't even have to worry about carbon. This is a -2, so that's a -6 total. That means +6 for that cobalt. And this is a neutral compound. So we have to neutralize all of those negatives with a +6. Well, there are 2 of them. So that means each one has to be a +3. On this side, we got 0. So what's the change in oxidation state? +3 to 0. Right? D is the answer. Let's see, 12 and 13. The minimum combined kinetic energy reactant particles must possess in order for their collisions to result in a reaction is called what? This is a definition. The minimum amount of energy required. Remember our energy diagram. This is reaction progress. This is energy. I'm going to say we've got energy here, we've got reactants here. and we got products over here. And we have to add enough energy to those reactants to get them over that hump. Then they can complete the journey to the products. The amount of energy in here is activation energy. The minimum amount of energy to get them over that hump, that energy hump. Once they get here, then they can go down the other side and make products. All right. (13). Whether a reaction is exothermic or endothermic is determined by, is it determined by activation energy? No. It's determined by starting point and ending point in energy. It's not determined by the physical state. That doesn't matter. For our calculations, it doesn't. C, how reactant and product potential energies compare. That's the key. And D, catalyst. Catalyst has only an effect on the activation energy. Right? It doesn't affect the starting energy and the ending energy. If you have so much energy in your reactants, and then you have this much energy in your products, remember, we have to conserve energy in a chemical reaction. So if it's got energy here and you put enough energy into it to make products, then you go up here with that activation energy, but how much energy do you get back? You only get this much back. You don't get all of it back. So that means you put energy in a certain amount, but you only got a little bit back. That means the difference between this one and this one is the enthalpy of the reaction, the heat that you put in. And the value is going to be positive because you put energy in, but you didn't get all of it back. So you lost some to the process. You put it in, you added it to the reaction, and you didn't get all of it back. So this difference is tells us that this is endothermic. You put more energy in endo than you got back. If it's the other way around, then you put a little bit of energy in and you get a whole lot back. That's exothermic. Out of. Exo means out of. You got energy out of that process. All right. So the answer to it is C. All right. 13, 14, and 15. We're still in chapter 9. Which of the following changes is most likely to decrease reaction rate for the chemical reaction? So we have 2 carbon monoxide and 1 oxygen yields 2 carbon dioxide. Let's see if that's balanced. Let's see, 2 plus 2 is 4, and 2 times 2 is 4. 2 carbons, 2 carbons. Okay, that's balanced. Which of the following changes will most likely decrease reaction rate? So think about the things that can cause a reaction rate to go faster or slower. Right? Well, these are all gases. Right? Carbon monoxide, oxygen gas, carbon dioxide. Right? So particle size has nothing to do with it. Right? We're not talking about solids. We're not talking about liquids where you can change the concentration. How do you change the rate of a gas reaction? That's the key. So how about A? Adding twice as much oxygen to the reaction mixture. What would that do? If you add twice as much oxygen, you're going to increase the rate because you've got more reactants there. to combine with the carbon monoxide. That increases. So A is an increase in rate. How about B? Tripling the temperature of the reaction mixture. Tripling the temperature should increase the rate because you're giving these reactants more energy. More of them now are at or above activation energy. And activation energy determines rate. So if you increase their energy, you can get over that hump with more of them. That increases the rate. How about C? Adding catalyst to the reaction mixture. A catalyst, by definition, increases the reaction rate. So by process of elimination, D should be the answer. It should be decrease in rate, removing some CO from the reaction mixture. Right. If you remove some of that, now there are fewer of these molecules to react with the oxygens, and the reaction rate slows. All right, so D is the answer. We got 15. Another catalyst question. Catalysts are correctly characterized by each of the following statements, except one. All right, so how about A? They can be either solid, liquid, or gas. Is that true? Yeah. Catalysts can be any one of those. How about the second one? They lower the activation energy for a reaction. Is that true? Yes, it is. That's why the reaction speeds up. Because now, with that catalyst, more of the reactants have sufficient energy to make it over the hump and make products. How about C? Adding a catalyst to the reaction mixture. Oh, excuse me. I'm looking at 14. 15. They do not actively participate in the reaction. That's false. Catalysts do participate in the reaction. It's just that they are not consumed by the reaction. In other words, a catalyst comes in one side and shows up on the other side. It participates in the reaction, but it's not part of the product, the desired product. The catalyst goes in one, comes out the same. All right, so C is the false one. And D, removing some C. They are not consumed in a reaction. That's true. They're not consumed in a reaction. All right. Let's see if we can get all this one on there. Yeah. 17. All right. Which of the following is the correct equilibrium constant expression for the reaction? All right. So let's write our reaction out. 4HCl, hydrogen chloride. Remember, when that's a gas, we name it by the convention hydrogen chloride. What would we name it if it's in aqueous solution? Then it becomes an acid, and we name it with the acid convention, hydrochloric acid. But as a gas, it's hydrogen chloride. Okay, and we need 2 waters. This is water vapor. That's a gas. And 2 chlorine molecules. All right, let's see. Is that balanced? 4 hydrogens, 4 hydrogens. 4 chlorines, 4 chlorines. 2 oxygens, 2 oxygens. Okay, we're balanced. And in order to write the equilibrium expression, the equilibrium constant expression, the equation must be balanced. The next question is, do we have any pure liquids or solids in this? No, we don't. They're all gases. So we use every term in the balanced equation to write our expression. So now, KEQ, let's write it over here. Equals what? Well, we use products in the numerator raised to the coefficient power There we go. And in the denominator, we put the reactants. So we have HCl, 4 to the 4th power, and oxygen to the 1st power. All right. So that makes C the correct answer. Let's see, let me check it. Yep, C is the correct answer. All right, 17, 18, and 19, and then 20s just around the corner. 18. Le Chatelier's principle. That was going to be the lab today, the one that you're going to have to do using the demo video. Le Chatelier's principle states what? Well, Le Chatelier said that if you have a system that is in equilibrium, any kind of system, we're going to focus on chemical systems, of course. So if you have a reaction that's in equilibrium, and we just wrote the expression for the equilibrium for that balanced equation, if you do anything to disturb that equilibrium, the system, the chemical system, will respond in such a way as to reduce that stress. Okay, so let's see which one of these fits. Only exothermic reactions reach chemical equilibrium. It doesn't have anything to do with whether it's exothermic or endothermic. It works on either one. B, only reactions in which a catalyst is present can reach chemical equilibrium. Well, that's as false as it can be, because the catalyst only affects the speed that it reaches equilibrium. It doesn't affect the actual equilibrium. So a reaction that has a catalyst introduced will still have the exact same equilibrium expression for the K value, whether it's got a catalyst or not. C, if a chemical equilibrium is disturbed, the system will try and reestablish equilibrium. That's a pretty good expression. That sounds like Le Chatelier to me. So I think C is the answer. We'll check D just to be sure. If a chemical equilibrium is disturbed, the temperature of the system will always decrease. No, not necessarily. So we were right. C is the answer to that one. 19. 19. Carbon dioxide and hydrogen are allowed to react until an equilibrium is established as follows. Okay, so this is our ruling equation. CO2 plus hydrogen. And notice we write that double barbed arrow to mean that we can establish an equilibrium here. Makes water, let's see, how about the phases? We probably ought to put the phases in there. Carbon monoxide. This is a gas, and this is a gas. So this is an entirely gas reaction, which means we use every expression. What will be the effect on the equilibrium of removing carbon monoxide from the equilibrium? This is established at equilibrium now. What are we going to do to it? We're going to remove some of this. What's going to happen? The system, the reaction system, is going to respond in such a way as to replace as much of that carbon monoxide as possible. So it will shift from left to right to replace some of this and consume some carbon dioxide and hydrogen. It'll make more water, and it'll make some carbon monoxide. So let's see which one of these expressions is accurate. The equilibrium will favor the side of the reactant molecules. No, it'll favor the product side. B, hydrogen concentration will double. No, we don't know what will be the actual change, but it won't double. It'll decrease a certain amount. How about C? Carbon monoxide and carbon dioxide concentrations will double. No, you can't do that. Not if you let the reaction reestablish equilibrium. It has to consume some. This will go down, this will go up. And D, hydrogen concentrations will decrease. Correct. And water concentrations will increase. Correct. D is the answer. I had a thought there for a second. Let me see if I can retrieve it. It's gone. If I think of it, I'll bring it back up. All right, so I think 20 is waiting for us. Le Chatelier's principle again. Which of the following changes will shift the position of the equilibrium to the left for the reaction? All right, so we have nitrogen and hydrogen. Oh, this is the Haber-Bosch process. Nitrogen gas plus 3 hydrogens, gas, yield NH3, ammonia, gas, plus heat. Okay, is that balanced? 2 nitrogens, 2 nitrogens, 6 hydrogens, 6 hydrogens. Okay, when we put heat on this side, what does that mean in chemical terms? It means that this is exothermic. That is, heat is a product. This reaction gives off heat. All right. Now, which of these changes will shift the position of the equilibrium to the left for this reaction? Well, let's see. We could add nitrogen, we could add hydrogen, we could remove ammonia, we could cool it, we could remove heat, and that would bring it this way. Treat heat as a product. And if you add heat, it'll go that way. If you remove heat, it'll go that way. How do we do that? With temperature. So let's see which one works. We want to shift the position of the equilibrium to the left. So what do we want to do? Double the concentration of nitrogen. Nope, that goes the wrong direction. Decrease the concentration of ammonia. That'll go to the right. Increase the concentration of hydrogen. That'll go to the right. Triple the temperature. Add heat. Add heat to this side, drives the reaction that way. Okay? Now that may seem counterintuitive because we said before that we need to add energy to make more reactant, more of the reactants with sufficient activation energy. Right? So if we add heat, we should have more of these with activation energy. But Le Chatelier contradicts that and says it'll actually move to the left because heat is a product. Okay? And that's true. Both are true. If we increase the temperature, more reactants have enough activation energy. But we also add heat, which shifts to the left. So that was the problem that Fritz Haber had when he was working on this process. So how did he solve it? Well, he did 2 things. He added a catalyst, which made the reaction go faster to the right. Now, it didn't change the equilibrium, but it did get things happening much faster. He used a catalyst. It was iron, finely divided iron. But how he shifted to the right, he bled off. he bled off some of the gases as the process was continuing, and it cooled them. So what happens then? The boiling point of nitrogen is very, very low, and hydrogen is very, very low. Ammonia is much higher. So he only had to cool it a little bit. This would come off as a liquid, and these would stay gases, and he'd run them back through the reactor. So what was he doing? He was removing product. He was removing this, which actually drove the reaction this direction, in spite of the fact that there was heat there. Okay, and it was happening a lot faster. So the end result is he was able to produce ammonia in sufficient economic quantities with that process. Even though Le Chatelier was against him. All right, 22. Oh, I didn't write the number on that one, did I? Back up. That was 20. Okay. Now we'll go to 22. Okay. In which of the following compounds does chlorine have an oxidation number of +5? So let's see. We got 3 actual answers and then 2 combination answers, more than one correct response or no correct response. So what that means is we got to do all 3 of them. So let's see. A is HClO. If we put that in aqueous solution, that would be hypochlorous acid. We're looking for chlorine. Okay, so this one's +1, +1. This one's +2. So that means together those are +3, and chlorine has to balance that with a -3. Right? So that's not the answer. We're looking for +5. How about potassium chlorite? Let's see. Potassium is an alkali metal. It's always +1. Oxygen's -2, so that's a -4, and this is a +1. Together that makes -3, so this is a +3. Is that right? Let me see. -4 +1. Yeah, that's right. Ah, that was a -3. This is a +3. C. Calcium ClO3. This is calcium chlorate. All right. So when you have a subscript outside of parentheses, it has to propagate through the entire contents of that parentheses. So if we have a -2 here and a -1 there, this is a -6 total. And then a -1. So that is a -7 times 2 is a -14. Right? And then a +2. Oh, wait a minute. I'm sorry. That's not right. We're looking for chlorine. Let's start over again. -2 for that one. So it's 3 times 2 is a -6. 2 of them makes a -12, but we got 2 pluses here. So a +2 makes a -10. There we go. Now that chlorine has to balance this -10. So you've got 2 chlorines here. 2 chlorines. has to be a plus 10 to balance that. So each one of these has to be a plus 5. There's your answer right there. C is the answer. Not more than one and not no correct. It's C is the only answer. 23 and 24. In which of the following sequences of sulfur-containing ions are the ions arranged in order of decreasing oxidation number of sulfur? Decreasing oxidation. So that could be from a positive number to a less positive number. It could be from a positive number to a negative number. Or it could be from a negative number to a more negative number. All we need is a decreasing value. So which ones do we have? We've got sulfite ion. Let's just put them out here. We have a sulfate ion. We have a sulfide. What else do we have? We have S203, 2 minus. That's called thiosulfate. And that's it. We just need to do the oxidation number for each one of these sulfurs. All right, so this is a -2 times 3 is a -6, but we're holding out 2 minuses for the charge. -4. That makes this +4. Okay, how about this one? -2 again. -8 total. Hold 2 out. -6. That means this is a +6. This one is a 2 minus. The charge on an element, a free element like that, if it has a charge, is the oxidation number. And this one, 3 times 2 minus is -6. Hold 2 minuses out, -4. So that's a +4. Each one has to be a +2. Okay. So we want to put them in order of decreasing oxidation number. So what's the biggest one on here? This one. So this one's first. And then the next one, smallest one, is this one. And then the next one is this one. And the last one is sulfide. Okay. Let's see. Start off with sulfate. Sulfate. Thiosulfate. Oh. The answer doesn't have all of them in there, right? So the one that works is this one, and this one are in the correct order. A is in the wrong order for these two. And C is in the wrong order, putting this one first ahead of that one. Okay. So we were only looking at 3 of the possibilities. And B is the best answer. Right. Let me do it. No, let's try it this way. There we go. B is the best answer. 24. Which of the following reactions is a non-redox reaction? Okay, so we have multiple choices at the bottom, more than one or none correct. All right, we got to do all 3 of them. So let's do A over here. First one, calcium carbonate yields calcium oxide plus carbon dioxide. Is that a redox reaction? Well, let's see. Calcium is an alkaline earth. It's always a 2+. Oxygen is a 2 minus. So that's a 6 minus. And a 2+. is 4 minus, which makes this one a 4 plus. Calcium is still a 2 plus. Oxygen still a 2 minus. Carbon, let's see, this one is 2 minus, so it's 4 minus total, 4 plus for this one. Right? That's a non-redox reaction. A is a good answer. How about B? Excuse me. Yes, B. Okay. Reaction for B. 2 potassium chlorate. Okay. Makes 2 KCl plus an oxygen, 3 oxygens. Just checking for balance. Yeah, it's balanced. Okay, potassium is a +1. Oxygen's -2. So let's see, this is -6 total, and a +1 means -5. Chlorine is a +5. On this side, +1 and -1. All right, we got our answer. 2 different ways we can get an answer to this one. One is chlorine obviously went from +5 to -1. Oxygen went from -2 to 0. But there's a rule, a trick. If you've got one of your elements is over here, free element, which makes it 0, but it's in a compound on this side, that's automatically a redox reaction. So if the element's on this side and it's in a compound on that side, same thing. So either way, we can produce this one as a redox. Right? So that's not, we're looking for non-redox. So let's look at the next one. How about C? C, SO3, 3 plus water, is it? Yep. H2SO4. Okay. This is a 2 minus. This is a +1. This is a 2 minus. -6. That makes this +6. This is +1. So that's a +2 here. This is a -2. So that's a -8 here. That's a -6. That means this has to be a +6. This is also non-redox. A and C are not redox reactions. That's why D is the answer, because there's more than one of them. All right. Who's next? We're still in chapter 9. 25, and then we'll get 27. 25 and 6. Which of the following statements concerning oxidation reduction is correct? About A, they cannot occur independently of each other. That one is definitely true. They always occur together. Reduction and oxidation must match, in fact, the number of electrons that are moved. Each one must be equal. If the oxidation step loses 4 electrons, the reduction step must gain 4 electrons. How about B? They accompany all chemical reactions. We just proved that one is wrong. How about C? They describe respectively the gain and loss of electrons, oxidation, reduction. No, this is gain. This is loss. They got it backwards. So C is wrong. So there's only one correct answer, and that's A. (26) In the redox reaction, 4Fe3O2 3O2 plus 12 HCl. And we're told this was redox. 4FeCl3 plus 6 water. Okay, is that everybody? That's everybody. Okay, 4 irons, 4 irons. 6 oxygens, 6 oxygens. 12 hydrogens, 12 hydrogens. 12 chlorines. 3 times 4 is 12 chlorines. That's balanced. And we know it's redox. They told us it was. But we've got an element here, and it's in a compound here. So we know this is redox. So which one of these statements is good? Okay, it's asking for oxidation reduction particulars. All right, so we're going to have to do, that's 0. That's 0. This is +1, -1. This one is -1. Whenever you have chlorine combined with a metal, something else, we usually give chlorine a -1. Rather than, like we did in a previous question, we calculated the value for chlorine. But in this case, we're going to give it a -1, which means this is a +3. And this is a -2 and a +1. Okay, so what happened here? Well, iron, what did it do? It lost 3 electrons per iron. Okay. Oxygen probably did something. Right here. Oxygen gained 2 electrons per oxygen atom. Okay. Now, since we had 4 irons in this process, that means we had 12 electrons lost. And oxygen, we had 6 oxygens equals 12 electrons gained, lost, gained. Okay, now maybe we can answer some questions. 26. HCl is the reducing agent. Did HCl do anything? No. HCl didn't do anything. So it's not an oxidizing agent. It's not a reducing agent. It's nothing. So A's wrong. How about B? Oxygen is the substance oxidized. Oxygen went from 0 to -2. No, it was reduced. Oxygen was reduced. How about C? Iron undergoes an oxidation number decrease of 3 units per atom. It went from 0 to plus. Its oxidation number increased from 0 to +3. So C is wrong. Right? They're all wrong. Right? E's the answer. There's no right answer in that. 27 and 28. All right. In a redox reaction, the oxidizing agent is the substance reduced. It gains electrons. So C, that contains an element that undergoes a decrease in oxidation number. If an oxidation number decreases, you have to gain electrons. You go negative. Add negatives, and you go negative. Right? So C is the answer to this one. 28. For a collision between molecules to result in a reaction, Pause just a second. I need to look at something. Okay. Let's see. There we go. Okay, for a collision between molecules to result in reaction, the molecules must possess a certain minimum energy. We did that one before, didn't we? And minimum of energy and exchange electrons? Not necessarily, right? That means it's redox, right? And we've already proven that some reactions are non-redox. Interact with a catalyst for at least 1 second. Well, maybe there's no catalyst there, right? The reaction could still occur. Let's see. C, have a favorable orientation relative to each other when they collide. Exactly right. When you get a collision, this is the collision model. When you get a collision, you must have a minimum amount of energy, and you must have the proper orientation. Those three conditions must be met for a reaction to occur. So C is, C is the right answer for this one. There's only one correct answer. 31. Chemical equilibrium is reached in a system when complete conversion of reactants to products has occurred. No, there's no equilibrium then. If you don't have some reactants left over, there's no equilibrium. So that one's wrong. How about B? Reactant and product concentrations are equal. Not necessarily. They can be different. And very often are. Reactants are being consumed at the same rate reactants are being consumed at the same rate they are being produced. Okay, I see what they're saying there. A plus B, C plus D. They're being consumed on this route over here. They're being produced on that route. If these two rates are exactly the same, they're equal, then you get equilibrium. That's why C is the answer. Yeah, we can get all those. 34 and 35. According to Le Chatelier's principle, which of the following effects will occur if ammonia is removed from an equilibrium mixture governed by this equation? If we remove ammonia from that equation, I've already written up here once, I'm not going to write it again. If you remove a product, the reaction shifts toward the products. Concentration of N2 will increase? No, that's reactant. Heat will be generated. Yes, heat will be generated because it is a product and we're shifting toward products. So B is correct. C, concentrations of hydrogen will decrease. Yes, we're shifting toward products and consuming reactants. So more than one correct response is the answer. D is the answer. 35. For which of the following equilibrium systems will the equilibrium position shift to the left when a stress of increased pressure from a volume decrease is applied? Okay, now we're talking about how do gases behave. I guess I better write these. We're looking for shift to the left. Shift left for pressure increase by a volume decrease. Okay, so let's just take it this way. The way to understand this problem is to look at how many moles in the balanced equations, how many moles of reactants yield how many moles of product. They're all gases. Yes, 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 they're all gases. So for the first one, how many reactant moles do we have? We have 9 moles. Yields what? 6 moles. If we increase the pressure, let's see, increase the pressure by decreasing the volume, then this one is going to shift to a smaller number of moles. We're increasing the pressure. Its response is to try to decrease the pressure. And you do that according to Avogadro, you do that by decreasing the number of moles of gas. So this one would shift to the right. Shift left, no. This one shifts right. How about B? 2 moles here yield how many here? 2 moles. If you've got the same number of moles on reactants and products, you can change the pressure any way you want. Change the volume, whatever. It will not affect the reaction. There's no way for this system to respond to accommodate that change in pressure. How about C? 2 moles gives you how many moles? 2 moles. Same reasoning as B. All right, so there are no correct answers here. All right. $39. This is one of those where we look at 3 statements and see how many of them are true. Right? Statement 1. The only information needed to write an equilibrium constant expression is a balanced chemical equation with physical state information for the reaction of concern. That is absolutely true. All you need is a balanced equation, and you need to know the states so that you don't put solids or pure liquids in there. Only gases, only solutions. Okay, 1 is true. How about 2? The oxidation number of sulfur is the same in the species H2SO4 and SO4 2-. What is this right here? That's the polyatomic ion, sulfate. Sulfur has to be the same oxidation number in both of them. That one's true. How about 3? Increasing the concentration of a reactant makes collisions between reactants and other reactants less likely because of more crowded conditions. No. Increasing the concentration of reactants increases the number of collisions. Right? So 3 is false. Right? So 1 and 2 are true. That means B is the answer. 2 of those statements are true. How about, let's see. All right, let's get 45 in here. Characterize each of the 3 given statements as being true. Oh, okay, another one of those. So let's look at 1. See if it's true. Of the known atmospheric gases, carbon dioxide is both the most abundant and also the most efficient of preventing heat loss from the earth. That is absolutely false. There are any number of gases that are more efficient, and carbon dioxide concentration is about, right now, in the neighborhood of 400 parts per million. Right? When I was a kid, it was in the neighborhood of 320 to 330. Right? So it's going up, but it's not the most abundant either. The most abundant greenhouse gas in the atmosphere right now is water. Right? So that one's false. All right, how about 2? Ozone is a form of oxygen in which there are 3 atoms per molecule. That is absolutely true. That's ozone. How about 3? A decrease in body temperature slows down the rate of chemical reactions. That is also true. The rule of thumb is reaction rate doubles for every change in temperature equal to 10 degrees C. That's a rule of thumb. It's not exact, right? But it does show that the reaction rate increases with temperature. So 2 and 3 are true. That means B is the answer. 46. Assign the following reaction to one of the reaction classifications given in the response list. Okay. 2NO2 plus H2O2 yields 2HNO3. Okay. You got 2 simples on this side, make them more complex on that side. This is a combination reaction or a synthesis. Right? Combination is the one that fits for this. Answer is B. Oh, we got another one. Assign the following reaction to one of the classifications. All right. 49. Oops. 49. So we have potassium cyanide, hydrogen chloride, hydrogen cyanide, and potassium chloride. Okay. Notice here, this is a polyatomic ion. So this is A, B, C, D. What we're doing is we're swapping places, this one with that one. Or you could look at it the other way, swapping this one with that one. But anyway, we get this one now paired with chlorine, and this one now paired with hydrogen. That's a double replacement reaction, or an exchange. Okay, so D is the answer for that one. All right. Oh, we're still in chapter 9. Okay, 52. For the indicated element, select the correct oxidation number for the response list. Sulfur in H2SO4. Remember, we could do it that way, or we could do it this way. Right? Either way works. They're exactly the same oxidation number. So let's do it this way. This is a -2, so a -8 total, but we want to hold 2 out. -6. Sulfur is a +6. D is the answer. 53. All right. Let's see. Oxidation number of carbon in potassium hydrogen carbonate. So hydrogen carbonate is a polyatomic ion, right? There we go. So we can calculate for either one. We'll do it for this one. So we have -2 here times that, 6. And we're looking for carbon. Yeah. So hydrogen is +1 and potassium is a +1. So -6 and 2 pluses is a -4. This is a +4 for carbon. C is the answer. Looking for the oxidizing agent in 56. So here's our equation. Sulfur trioxide and nitrogen monoxide. Sulfur dioxide, nitrogen dioxide, sulfur trioxide, and nitrogen monoxide. We want the oxidizing agent. Which one is reduced? So we want the one that is reduced. Okay. Let's start off here. -2 for oxygen. -4, so that means +4 here. -2 +4. Excuse me. -4. This nitrogen is also a +4. This is -2 times 3 is -6, so this is +6. And this is -2, that means this is +2. So, which one was reduced? Which one decreased their oxidation number? Well, sulfur went from +4 to +6, that increased, right? So it was oxidized. We want the one that was reduced, which is nitrogen, right? It lost 2 electrons per nitrogen. There's your answer, right? NO2 is the oxidizing agent. Okay, 62. For the following general reaction equation, choose the correct form of the equilibrium constant expression from the response list. Okay, so here we have 2 X's that are gas plus 3 Y's that are solid, and then it produces 2 Z's that are gas. Okay, so this one is going to be left out. Let's see, is that? Yeah, okay. This one's got to be left out. So the K value here is going to be Z squared and X squared. Now, any like that? Z squared over X squared? Yeah, that's B. B is the answer. By the way, we could also write this one as right? Mathematically speaking, those are identical. Let's see, who's next? 64. Consider the following equilibrium. Determine the effect on the position of equilibrium when some CO2 is removed. So we're going to remove CO2. Which side is CO2 on? CO2 is a reactant. So if we remove the reactant, the reaction shifts to the left. Answer is B. That's easy. Too easy. $66 and $7. Oh, okay. So we're going to use the same reaction again. All right. Determine the effect on the position when a catalyst is added. Does not shift. Catalyst has no effect on equilibrium. It only has effect on the rate of reaction. Right? So C is the answer for this one. No effect from a catalyst. No effect on the equilibrium from a catalyst. What if volume of the container is increased, pressure is decreased? So pressure is decreased, volume is increased. So we need to look at what's the gas balance on either side. Right? The gas on the product side is total of 4 moles of gas. And that's in equilibrium with 2 moles. So if we decrease the pressure, if we expand the volume, then in order to compensate, the reaction is going to try to make more gas molecules, more moles of gas. It will shift to the left. So B is the answer. All right, we're finally in chapter 10. Okay, chapter 10, number 3, and let's see, we get 3 and 4 on there. Number 3. In the reaction, N3 minus plus H2O yields HN3 plus OH minus. The Bronsted-Lowry base is. Okay, I better write this one on the board. N3 minus plus H2O yields HN3 plus OH minus. Okay. Bronsted-Lowry defined the base as the one that accepts the proton. So which one accepted the proton here? Well, notice this one went to here. It accepted the proton. So that's the base. A is the answer. N3 is the base. Which of the following is not a conjugate acid-base pair? All right. What's that? 4? Yep. 4. Not a conjugate acid-base pair. What do you have to have for a conjugate acid-base pair? Well, the acid has to have a proton that can be given up. And then the base must be the result of one proton being lost from that molecule. So how about this one? NH4 and NH3. Oops, put my 4 in the wrong place. There we go. Well, yeah, it lost one proton to go from here to here. That one's correct. Let's see, A is correct. How about B? OH minus and O2 minus. Excuse me, O2 minus. There we go. Yeah, it lost that proton. And it left behind an electron, which made this 2 minus instead of 1 minus. That's correct also. How about C? H3PO4 and H2PO4 minus. Yeah, lost the proton, went from here, and the charge stayed behind, the negative stayed behind. That's true. How about D? Let's see, CO2 and CO3 minus. CO2 and CO3 minus, right? The first thing that's wrong with this one is there's no hydrogen, right? So we throw this one out because it has no hydrogen. So what has it done? It actually added an oxygen. So that's not an acid-base pair. D is the answer. It's the wrong one. All right, we got a 5. Yeah, we got a 5. Okay. In which of the following pairs of acids are both members of the pair strong acids? Okay. Let's just list the strong acids that we were given in the discussion earlier. Right. HCl, HNO3, H2SO4. I think those were the ones. But you can also have HBr and HI. Those are strong acids. You can have HClO4. Perchloric acid is very strong. So let's see, which are both strong acids. H3PO4 is a weak acid. So A is not it. HI and HNO3, yes. That's true. H2CO3 is carbonic acid. It's very weak. And C2H3O2 is acetic acid, vinegar. It's very weak also. Right. So B is the only possible answer for that. All right, 5, 6, and 7. In which of the following pairs of acids are both members of the pair polyprotic? All you need is to be sure it's an acid. It's got these protons that can be given up, and there's 2 or more of them. So which one satisfies polyprotic, right? A is diprotic monoprotic, B is monoprotic diprotic, C is monoprotic triprotic, and D is triprotic diprotic. D is the answer. Poly just means many, 2 or more. So D satisfies. Seven. Which of the following is produced? Which of the following is produced in the first step of the dissociation of H3PO4? H3PO4 would produce, remember, 1 proton at a time. What's left over? Well, we left a negative behind. So whatever's left behind must be a negative charge. Right? So B is the answer. Okay. That's the conjugate base of phosphoric acid. All right. $11. A solution with a pH of 13.3 is what? Well, remember the pH scale? Right? pH. 7 is neutral. Anything higher than 7 is basic. Anything lower than 7 is acidic. Right? So 13.3 says it's basic. In fact, it's very strongly basic. Right? So D is the answer to that one. All right, 12 and 13. Which of the following does not describe an acidic solution? All right, let's see. The pH is less than 7. Is that acidic? Yeah, we just showed you. Definitely acidic. B, the hydroxide ion concentration is greater than 1 times 10 to the minus 7. If this is greater than 10 to the minus 7, then what would hydrogen be? Hydrogen would have to be less than 10 to the minus 7, right? Because when you multiply them together, you get 10 to the minus 14, always. So that means the balance is toward hydroxide, which makes it basic, right? This is not acidic. And we found our answer, really, right? Because we don't have any oddballs in there. We can look at the others and prove to ourselves that that one is the only one that is not acidic. 13. If the pH of a solution increases from 3.1 to 5.1, the hydronium ion concentration increases by a factor of what? If we go pH from 3.1 to 5.1, 3.1 to 5.1, it's becoming less acidic. So the hydronium ion concentration should decrease. So it can't be A and it can't be B because those are increases. So it's either C or D. So what's the difference between these two? Well, notice that their pH, that's a logarithmic scale. For every 1 pH equals 10 times the hydrogen ion concentration. So this goes 2 pHs and it goes the wrong direction. So it's actually a decrease in 1 pH is a 10th. So it decreases by a factor of 10 times 10, which is 100. Decreases by a factor of 100. That's why D is the answer. 14. In which of the following pairs of salts will both members of the pair hydrolyze in water to give solutions that are basic? Okay. All right. So here we have, sometimes we have, these are all salts. They're combinations of cations and anions. So what we're looking for is one that will react with water to take a hydrogen ion and leave a hydroxyl behind. We need some anion to react with water to yield that. Okay? So we need an anion that is actually a strong conjugate base of a weak acid. All right? So how about lithium chloride? Chlorine is derived from HCl. That's a strong acid. So that can't be. Right? So that one will not produce a basic solution. Right? Can't use that one. How about B? Ammonium chloride. That one's out. for the same reason. How about C? Sodium acetate. C2H3O2 is the strong conjugate base of a weak acid, acetic acid, and sodium fluoride. The hydrogen fluoride or hydrofluoric acid is weak. So this is a strong base. That one works. That will produce a basic solution for both of the salts. Let me see. Yeah, okay. If a solution is buffered at a pH of 9.5, 9.5 pH buffer, then the addition of a small amount of acid will cause the solution to have a pH of approximately 9.5. It won't be exact. It'll be off by some. It depends on how much acid you add. But it'll be very close to 9.5. That's the whole point of a buffer. 20. Determining the concentration of an acid using an acid-base titration always involves completely reacting a measured volume of an acid with a known volume of, well, I wouldn't say always, but if the case is a measured volume of acid with a known volume, well, that's true. That is true. One of them could be a known concentration and the other one could be the unknown, just whichever one. A base of known concentration. That's a good answer. We don't always know the exact concentration of the base or the indicator, and the concentration of the indicator doesn't matter. The indicator is just there to tell you when you've reached that point. So it's either A or B, and B, since B is a known concentration, we can change that concentration at will, as long as we know what it is. So it's just a base of a known concentration is the best answer. This is one of those cases where you have multiple choice and you've got to choose which is the best answer. It may not be the only answer, but is the best one that you're given. And A satisfies that condition. 24. All right. In which of the following pairs of acids are both members of the pair strong acids? All right, we looked at it earlier. HNO3 is a strong acid, but HNO2 is not. It's a weak acid. H2SO4, H2SO3. The first one's strong, second one is weak. C. HCl, hydrochloric acid, and perchloric acid are both very strong acids. C is the answer. (29) Which of the following indicates an acidic solution? Well, let's see. A, 7.5 is above 7, so that's basic. Can't be that one. B, H, a hydronium ion concentration of 10 to the minus 5. Ten to the minus 5. That is greater than 10 to the minus 7. Right? So the hydroxides would have to be somewhere in the neighborhood of 10 to the minus 9. Right? So this one is acidic. How about C? Hydroxide ion concentration of 10 to the minus 8. Yeah. Right? So hydrogen would have to be 10 to the minus 6. Or in that neighborhood. So yeah, that one's acidic too. So D is the answer. 2 of those are correct. $37. Let's see, which one of these are true? Both members of a Bronsted-Lowry conjugate acid-base pair must contain the element hydrogen. Not necessarily. Hydrochloric acid, right? It only has 1 proton, so its conjugate base is just the chloride ion, right? So 1 is false. How about 2? The larger the value of the acid ionization constant for an acid, the weaker the acid is. No, the larger the Ka, large means increased strength. Right? So that one's false. How about 3? Weak acids cannot completely neutralize strong bases. Well, that's as false as it can be, right? I can neutralize sodium hydroxide solution with acetic acid. No problem. Right? So all 3 of them are false. All right. How about 38? Formation of a coordinate covalent bond is always part of a Bronsted-Lowry acid-base reaction. Coordinate covalent bond. Okay. Say you have HF, put it in water. Well, all we need is one example where it's not true. When an acid dissociates like this, it ionizes, it breaks the bond, and then this one goes like that and leaves the electron behind. Right? So when this forms a bond with something, say it forms a bond with water, where do the electrons come from for the bond? They come all from the water, right? So that, in that case, we have a coordinate covalent bond. So 1 is a possibility. 1, maybe. 2, the compound H2CO3 is both a strong acid and a diprotic acid. No, it's not a strong acid. It's a weak acid. And C, the pH of a solution with OH minus equals 1 times 10 to the minus 8 is a 6. Right? So for 3, how do we do that? POH, let's do that one first. POH would equal negative log of 1 times 10 to the minus 8, which is equal to 8. So the pH would be 14 minus 8, which is 6. So that's true. So 1 must be true for 2 of the 3 statements to be true. Number 40. Let's see. I'm gonna have to break in a couple of minutes. Finish this afterwards. But that's not a problem because there's nobody here but me. In aqueous solution, Arrhenius acids undergo ionization and Arrhenius bases undergo dissociation. Let's see. Yeah, acids ionize, bases dissociate because they're already ionic compounds. That's true. 1 is true. How about 2? Production of a salt, NaNO3, through neutralization reaction involves the reaction of a weak acid with a strong base. Well, it would result from this plus this, correct? Right? 2 is false. That's a strong base and a strong acid. How about 3? The ion product constant for water at 24 degrees has the numerical value 1 times 10 to the minus 4, 14. That is a definition, and it's true. So we have two true statements there. 41. The two members of a Bronsted-Lowry conjugate acid-base pair will always differ from each other by 1 unit of charge. By 1 unit of charge. Yes. Yes, because when you lose a hydrogen, the hydrogen leaves a negative behind, and the negative goes to the conjugate base. Right? So they will differ by 1 unit of charge. That's true. Number 2, an equivalent of an ion is the molar amount of that ion needed to supply 1 mole of positive or negative charge. That's a definition. That's the definition of an equivalent. How about 3? In an acid-base titration, the indicator changes color when the reaction between it and the added acid is complete. Acid-base titration, the indicator changes color. Yes, right? When you have, well, ideally, the indicator changes color at the endpoint, which is as close as possible as we can get to the equivalence point. Okay, so they're all 3 true. 45. All rainfall, even in unpolluted areas, is acidic. That is absolutely true. And it's because carbon dioxide plus water yields carbonic acid. Always. So 1 is true. 2, blood plasma, interstitial fluid, and intercellular fluid, the 3 general types of body fluids, all contain electrolytes. That's true. Yeah, they do. They contain positive and negative ions. Those are electrolytes. 3, blood plasma is slightly acidic because ions it contains undergo hydrolysis. The fact of the matter is, blood plasma is basic, and it's buffered between the range of 7.35 and 7.45, right? Unless you're sick. If you've got a really bad condition, it could go acid or it could go basic, in which case your metabolic systems are going to be in big trouble. And they'll be in bigger trouble the farther away you are from that range. How about 49? Select from the response list the compound or ion that best fits the description, reacts with hydronium to form HPO4 2-. Okay, reacts with hydronium. Okay, so this is a reactant, and it produces HPO4-, HPO4-. So all of those compounds have phosphate in them, right? So we need a phosphate over here. Oops. PO4. How many hydrogens? Well, if it gained a hydrogen from this one to make that one, then it must be, let's see, oh, 2-. There we go. 3-. If it gained a hydrogen from this one, then that would make this 1 less negative and make this one water. So it reacts with phosphate ion, PO4 3-. All right, I got about 5 minutes left before I have to break. 54. Select from the response list for the acid that best fits the description. An acid that has more non-acidic hydrogens than acidic hydrogens. All right. So hydrochloric acid has no non-acidic acids, so it can't be it. Acetic acid, C2H3O2. This is acidic. These are non-acidic, right? So it has more non-acidics than acidic. That's true. For C, you've got 2 acidics and 2 non-acidics. And for D, you've got 2 acidics and no non-acidics. So B is the only one that answers that one correctly. 55. Select from the list best fits the description. An acid that completely dissociates in solution to produce negative ions with a charge of 1. Well, let's see. How about this one? HCl dissociates like that, completely. Right? B and C are both weak acids. And D dissociates in a solution to produce negative ions with a charge of 1. Negative ions for, well, H2SO4 produces this one plus this one, which would be technically correct. But then this one also dissociates to this one and this one. Right, so it produces both, and the best answer would be A. All right, 2 more minutes, 56. Select from the response list the compound that best fits the description. A salt whose dissociation produces equal amounts of 2 ions. Equal amounts. A salt whose dissociation. All right. First, it has to be a salt. KOH dissociates into equal amounts of positive and negative ions, but it's not a salt. So sodium nitrate does dissociate. Yeah, that one works. H3PO4 produces uneven amounts, 3 hydrogens and only 1 phosphate, which is an acid, so it doesn't work either. Potassium phosphate produces 3 potassiums and only 1 phosphate. Right. So B is the only possible answer that fits both conditions. Let's see, how many more do we have to go? Let's see if I can get them all in before I have to break. 71. What's the pH of a buffer that is 0.250 in weak acid? So this concentration is 0.250 molar, correct? And 0.260 molar in the conjugate base. Okay? And the pKa of the acid is 5.53. This problem is screaming for the I just lost it. Henderson-Hasselbalch equation. Okay, so the pH is equal to the pKa plus the log of the conjugate base divided by the acid. Right. So we just need to fill in these values. 5.53 plus the log of 0.260, 0.250, and find out what that mathematical expression produces. 0.26, enter 0.25, divide, take the log, and 5.53 plus. So that is 5.55 pH. C is the answer. That was simple. And that was the last one.